Okay, so welcome back to particle physics and the standard model. This is lecture 12. Good. So last time we started looking at the angular momentum in quantum mechanics as a segue to continuous symmetries, right? And we saw that you cannot measure the different components of angular momentum simultaneously. The two things that you can measure are the total angular momentum, in fact it is L squared, and one of the components that we take to be the Z component without loss of generality, right. And we also saw what the eigenvalues of L square were, it is L times L plus 1, and the eigenvalues of Lz that are integer values that vary from minus L to plus L, right. There are 2 L plus 1 eigenvalues. Now let us take this further. This quantized version of angular momentum gives rise to another very quantum concept, uniquely quantum concept called spin angular momentum, right. This we call it spin, but really there is no classical analog. At least angular momentum has a classical analog, right, and then we seem to quantize it. But spin is very much a quantum thing. The reason we call it spin is because this entity behaves like the orbital angular momentum, okay, as far as its eigenvalues are concerned, as far as its commutation relations are concerned, and so on. So it looks like it is another kind of angular momentum, okay. So all right, so that means we again have an S square operator which is an S dot S, okay. What are the eigenvalues of S square? Just like L times L plus 1, we now have S times S plus 1, small s, alright. So this is a capital S, this is a small s, okay. And what values can S take in general? They take half integer values, correct. That is what makes it distinct from the orbital angular momentum, which took whole integer values, right. And similarly I have all the commutation relations just like the orbital angular momentum, and that would mean I can measure S square and any component of the spin angular momentum, and without loss of generality I am going to take Sz as the component that I can measure along with S square simultaneously, alright. So what are the eigenvalues of Sz then? I can now write this as Ms, and Ms takes on values minus S plus 1 and so on, passing through 0 again all the way to S minus 1. In this case let me be a little clear, actually this was a mistake. So this time it need not pass through 0. Why? Because S is a half integer, right, need not, right. Over here it had to because L was a whole number, but S is not a whole number, good. So S minus 1 and S, again how many values? In exact analogy with this we have 2S plus 1, okay. Again these are all small s, alright. So don't get confused, capital S is for the operator and small s is for the eigenvalues, okay, good. Now I have been saying throughout the course so far that fermions are spin half, bosons are spin 0 or spin 1 and so on, right. And you have probably taken it for granted as well, you must have heard this as well, correct? But there are a couple of counterintuitive things here that we just take for granted, alright. For instance, by just stating that fermions are spin 0, fermions are spin half and bosons are spin 1, 0 and so on, we are assuming that the spin of that quantum state which we are describing as the particle is fixed, correct? We are not actually explicitly saying this, but we are just assuming it. That is because it is true, right? But it is a very remarkable thing that for a particle species S is fixed. Okay, but not only that, here is the thing, right? When we actually say fermion, right, in quantum mechanics, what is a fermion? We don't talk about spin in quantum mechanics, correct? In quantum mechanics, a fermion is an entity for which under exchange, right, if I have two fermions with wave function psi 1 and psi 2, under exchange what happens? They pick up a minus sign, correct? This is what is actually a fermion that we learned in quantum mechanics, right? So, what is this? This is the Pauli's exclusion principle, correct? And what if it does not pick up a minus sign under exchange? That is a boson, right? This is what are the actual definitions of a fermion and a boson, right? Now, suddenly we made this leap in our speech saying that spin half is or spin 3/2 is a fermion, and integer spin states are bosons. So, why did we say this? That is because we made use of a theorem that we use unconsciously all the time. It is called the spin statistics theorem. Okay. This is a cornerstone of quantum field theory. Particle physics and so on. Okay. It just states exactly what I just said. It turns out that bosons are integer spin states, so that S is half, 1, 2 and so on. What is a spin 2 boson? The only spin 2 boson that could exist is a graviton, correct? And fermions are half integer spin states, right? So, S is half, 3/2, 5/2 and so on, right? Okay. So, on this side I have spin, on this side I have what is called statistics. Why is this called statistics? So, the antisymmetry or the symmetry under exchange is what leads to, so let me just write anti-symmetry or symmetry under exchange is what leads to occupation number of quantum states, right? Hence statistics, right? So, an energy state, an energy level for instance could be occupied by any number of bosons but only at most one fermion, right? That is where the occupation number notion comes from, and that is what is called statistics, right? Good. So this is a theorem, a very fundamental theorem of quantum field theory that we make use of. Okay, it's a very deep relation. So how do we know this is true? How are we relating these two concepts? So there are very many rigorous proofs, and I encourage you to go look at for proof, look at Srednicki or Schwartz or any number of online resources. Okay, but these are QFT textbooks. But here I am going to give you a cartoon proof to build some intuition for this. Okay, and the proof looks like this. All right, it's a very cartoon proof, so don't take it very seriously, but this is just to give you some intuition for why these two things can plausibly be the same. Okay, so this is a proof that I have seen in John Bayes' website. He's a mathematical physicist, but I find those very neat and help me understand the theorem better. So imagine that you had a ball, all right, with some strings attached to it. Okay. Now, now what do we know about fermions? What do we know about spin half particles? That they are described by states known as spinors. Correct? And what property of spinors do we know about? What is one property, what is one important property of spinors? It is that under 360-degree rotation, they pick up a minus sign. Correct? So if I rotate a fermion in real space by 360 degrees, it does not come back to itself, it picks up a minus sign. Okay? So that can be represented with this ball with strings attached. Alright, why is that? Here is why. If I were to turn this ball around by 360 degrees, okay, it is very likely that the strings attached to the ball do not stay the same way, but they get kind of entangled like this. Agreed? So if I were to draw more, then I can, they get entangled like this. So anybody familiar with using a mop with a twist in front would have seen this, right? When you twist the mop around 360 degrees, the ropes attached to the mop get entangled like this, right? And then if you twist this one more time in the same direction, okay, if you twist this one more time by 360 degrees, you might get it unentangled, right? So this entangled threads could represent the minus sign that you are picking up. Okay, it's just a cartoon, don't take this too serious, just think of this intuitively. Okay, so this is how if I do two 360-degree rotations, I come back to the same state. Alright, so that is the spin part of the spin statistics theorem. What about statistics, that is what about particle exchange? Okay, so it is like this now. Imagine that I have, let me try this. I have two balls with strings attached between them, that are at this point not entangled. Okay. But now if I exchanged these two in my hands, what could happen? It is quite possible now, in fact it almost always happens, that that they get entangled, right. This is under one exchange, right. So I am going to write it this way, under exchange. But then if I exchange it back, then once again I get the unentangled balls and threads, right. So again think of this as picking up a minus sign, which goes away when you go back to the when you re-exchange back, right. So that is kind of a cartoon proof that spinning your spinner by 360 degrees gets you back. So that takes care, that is what tells you that these are spin half or half integer spin states, and then if you take these half integer spin states and you exchange two of them, once again you pick up a minus sign and then you re-exchange, you get them back. So this kind of shows that spin and statistics are deeply related, right. So this happens only to half integer spin particles, right. Okay. So that is the spin statistics theorem. Let us move on and further explore the consequences of angular momentum and spin. Okay. So now we saw L and S. What else remains? There is always J, right, which is the total angular momentum, correct. Again this is a very quantum effect. Why? Because S is a quantum operator, right. Now in most systems what is conserved is the J. Well, I should not say most systems, in all systems, right. Especially when you are thinking of a system where L dot S is not 0, because if L dot S is 0, this is what I wanted to say in the beginning, then L and S are separately conserved. So J is also conserved in that case, but in particular L and S are separately conserved. But if there is an L dot S, in other words, if there is a spin orbit coupling, correct, this is spin, that is an orbital quantum number, right. In case you have that coupling, then you have to talk about the conservation of J in particle processes and other situations, right. So in classical mechanics, do you know of an analog for the spin orbit coupling? Is there any situation where the spin and the orbit actually interact, the spin of a system and the do they interact with each other? Well, we see this every day in the face of the moon, right. The face of the moon, there is only one face of the moon that we see every night, correct. Why is that? That is because of tidal locking, correct. Most systems, most binary systems more or less get into a tidal locking state, which is what gives them the highest stability, and this is why the spin of the moon and the orbit of the moon around the earth, over time, they have interacted, these two components of the Hamiltonian, and then you end up with a stable system, so that the spins, the moon's spin and its orbit are roughly the same period, they have the roughly the same period, correct. Okay. So, similar things can happen in quantum mechanics as well, right. You can have an L dot S which mimics the Zeeman effect, for instance. Okay. So, again more generally you also have if you want to add any two angular momenta, for instance if I want to add two spins, I can always do it as long as I make sure that I get sensible eigenvalues, right. So, I can add two spins, just writing an example as a more general addition of angular momenta. So, in a meson for instance, right, I have two spin half particles, and if I add them up, what is the total spin that I should get? It is not always 1, correct. I can get S as either 1 or 0, correct. Again y comes back to this and this, right. The z components add, but then the total can take on multiple values, the total spin. So, the total spin, if it is 1, we saw some examples, there is the rho meson, k star, phi, omega and so on. Spin 0 is of course the pion, kaon, the eta meson, eta prime and so on, correct. Okay. So, to generalize this again, we know that we can only add the total and z component of angular momentum operators J, L, S and all, right. So, we ask what is the J M state that we get if two states with a denoted by J1 M1 and J2 M2 are added. Right. So, in one of these is actually easily fixed, right. One of them is simply that if so M is just M1 plus M2 in this, why the z components just add up, correct. So, when we write a state in this way, we are talking about the two measurables here, total angular momentum and the z component, right, and the z components just add up. But J is not always J1 plus J2, right. Because J1 and J2 vectors may be oriented in multiple ways, correct. In other words, what are the values that are allowed for the total J? Again, go back to your quantum mechanics or go back to the earlier parts of this lecture or the earlier lecture. and you will be able to guess that the total values, sorry, all the values of the total j is j1 minus j2, or the absolute value of that, right, because either j1 or j2 might be larger, and then I add a 1 to that and so on until I get to j1 minus j2 minus 1, j1 plus j2 minus 1, and finally j1 plus j2, correct. And I leave you to add I leave you to count how many values of j can be obtained, right. So, this is how you obtain the, this is how you describe the state that you get by adding both the total and the z component of the angular momentum. Okay. These things turn out to be important for determining the quantum numbers of various bound states. Okay. When you go to PDG, the particle data group book, you will see such a host of mesons and baryons and so on, with all these bewildering numbers of j and k and so on. That is because all of that comes from this, okay, by adding the total angular momentum and the z components, you will get so many different possibilities, okay, and these are all realized in nature. That is the amazing part about it. It is not just things that you can write down, all of them are found in laboratories in the particle spectrum. Okay. Okay. So, what if I have 3 angular momenta? How do I add those? Not just 2. Well, you first start by adding 2, right, and then you look at the possibilities. You have all these possibilities for j, and then to this add one more, as simple as that. It is just a little more tedious, but that is the only way to do it. Okay. So, I will just say do 2, add one more state, right. Okay. So, so what are some consequences of this? That means baryons, right, which contain 3 quarks, like the neutron and the proton, right, always have half integer spin. Why? Because if I have 2 quarks, a 2 quark state will give me integer spin, right, and then I add a third quark, I go back to half integer spin, right, makes sense, correct. So, that means I can have baryons with total spin 3 halves, absolutely possible, okay, and those baryons are the ones that get on the baryon decuplet, which we touched about in the very first lecture, right, or maybe the second lecture. In any case, it is in Griffiths as well, Griffiths chapter 1 and chapter 2, right. And then the baryons with total spin half are the ones that go on the baryon octet that we had talked about. Okay. And of course, one hidden thing here is that this tells you again that mesons have integer spin. So, we already saw this, but it's once again hidden in this message, right. Spin 0, spin half and so on. But also the total j quantum number, right, of mesons with orbital angular momentum L, what could that be because of this addition? They can take on the values they take on the values L minus 1, L, L plus 1 and so on. Why is that? Because J is L plus S, correct, and then the total S is an integer. So, the total J also turns out to be integers exactly for this for mesons. Okay, so let me just write these are integers or whole numbers. Okay, total spin is also an integer value for mesons and total J is also an integer, just because the orbital angular momentum takes on integer values. Okay, good. So, we have built up some basics on how to count the total angular momentum, spin angular momentum of various composite states. So, I will end here. In the next lecture, we will see how these concepts can be reversed in a sense for other composite states, for such as atoms, in what is called the Klebsch-Gordon decomposition, and after that we will take up how spin states transform under rotations in real space, and we will look at the concept of spinors in quantum mechanics. Okay? And that will help us understand continuous symmetries as we go along. All right. So, I will end here. See you in next class. Thank you.